We're going to do an experiment where we measure Planck's constant using this apparatus, which is designed so that we can measure Planck's constant. Now, all it is 5 LEDs, and you know the wavelength of light emitted by each LED because it's written on it, power supply, and a voltmeter across the power supply, the LED, so you can measure the potential difference across the LED. And there's just a potentiometer here, so we can change what the potential difference is. So with a 660 nanometer LED, at a certain potential difference, it switches on. Lower than that, it doesn't. 620 nanometers, 595 nanometers, 565 nanometers, just about see that. And then finally 430 nanometers. See that down there? It's quite a bright room, so I don't know how good these results will be. But what we're going to do is we are going to measure the potential difference when the LED just turns on. And we're going to record that in a table, we can do some analysis, and from that we're going to determine Planck's constant. How does that work? Well, here's my dodgy schematic of an LED. It's just 2 extrinsic semiconductors, and every time an electron moves across from one part to the other, it's going to lose energy, and a photon is going to be emitted with an energy equal to the energy that the electron has lost. Now, if we connect a voltmeter across this junction, this extrinsic semiconductor junction, the potential difference across it is equal to the work that is done on the charge that's moving across that junction divided by the amount of charge. Remember that the volt is defined as 1 joule per coulomb. So if we rearrange that, so the energy that is transferred by charge moving through this junction is equal to QV. Q is the charge that's moving across it, so let's substitute the elementary charge, 1.602, let's use 1.6 times 10 to the negative 19 coulombs in there. V is what we're measuring, and so we will know the energy of the photons that are emitted for a particular potential difference. Okay, now the energy of the photon should be proportional to the frequency of the electromagnetic radiation. And the frequency, using C equals F lambda, is the speed of light, because it's light, divided by that wavelength. So we have the frequency, because the wavelengths are written on here. And we'll have the energy, because we'll know the potential difference when the LEDs switch on. Plotting a graph of E versus F will give us Planck's constant. So let's draw the table first. We're going to have the wavelength in nanometers, the frequency in hertz, which we'll calculate from the wavelength. That's our independent variable. Then our dependent variables. Well, we're going to have the potential difference when it turns on. Let's do a few of these. Oops, V2, V3, and then V average. And then from the average potential difference when it turns on, we're going to have the energy per photon, which we'll measure in joules. All right, let's draw some lines for this table. 1, 2, 3, 4, 5. I've only got 5 LEDs, so I'm only going to do 5 rows. I'm going to do this all in real time so you can see how quickly you can do this experiment, including drawing the table and everything else. Doesn't take long. Look at that, I'm using a ruler, but I'm also using a pen, which isn't great. I ought to be using a pencil in case I mess it up. Oh, very clumsy of me. One, 2, 3, 4, 5. Let's draw this there then. Okay, there's my table all set up. All that's left to do now is record some results. It's bad practice to write down any numbers that you haven't measured. Well, I've measured the LED wavelength by virtue of the fact it tells me on it. So let's start with 660 nanometers. We'll calculate the frequency later. Let's turn this knob until it just turns on. It's coming on quite a lower voltage than I thought it would, lower potential difference than I thought it would. You can just about see it coming on around about there-ish. So let's put down 1.40. Right, next one. We'll do repeats in a second. So next one is the 620 nanometers. coming on about there-ish. 1.52. All right, next one. Which one's that one? Yep, that's the 595 nanometers. Yeah, coming on about there-ish, 1.59. These all seem a little bit lower than I thought they should be. But okay, we'll go with it. Coming on about there-ish. 1.64, that's 565. And lastly, 430. Just about lighting. Wow, as high as that. My eyes aren't very sensitive to blue, so it's probably a little bit lower than that. But let's go with 2.98. 430. So there's the first set of results. Let's do them again. It's a little bit boring, I know, but we're doing it. 1.36. 1.50. This would work better in a dark room. So you could really see just when the LED comes on. 1.58. 1.66. It's around about there, 3.00. So you can just about see, around about there, the LED is just coming on. You might not be able to see it in the camera. Just starting to light at around about 3 volts. All right, third set. Off we go. Just starting to light about 1.32. Seems a bit lower than before, and I wanted it to go higher. Oh dear, these results aren't very good. 1.50. 1.59. 1.58, really? What's going on there then? No, it's not 1.58. I was seeing the, I saw the orange, but that's the background of the LED. It's a green LED. Focus. It's around about there. It's more like 1.63. And then about there, 2.97. Okay, let's turn it off. We have all our data. Now is the rather dull task of crunching numbers. So what we're going to do is the speed of light, c divided by that, but be careful because it's in nanometers. 3 times 10 to the 8 divided by, where's our fraction button? There it is. 660 times 10 to the power of -9. I hate using this calculator, really desperately hate it. Right, let's, don't like my column header there. Let's do frequency in 10 to the 14 hertz. Let's do that instead. So all I have to write is 4.5. Let's do 5.5. Let's do 3 significant figures. I'm not going to be able to plot more than 3 significant figures anyway. Is it possible to go through here and edit this? Yes. Ugh, horrible calculator. 4.84. Let's go into here and edit this. 959. Try again. 595. So 5.04. Horrible thing. 565. 5.31. And lastly, 430, 6.98, rounding correctly. So there we have that column. Now we need to calculate the mean of these. So 1.4, 1.36, 1.32, and then do divided by 3. Why is it giving it right? Okay, 1.36. Probably work that one out in my head. This one, again, I could probably work it out in my head, but let's do it. 1.5 at 1.5 at 1.52. Divided by 3. 1.51. No point having more significant figures than that. 1.59 at 1.58 at 1.5. Again, I could probably work this one out in my head. Divided by 3. 1.59. This one here. So 1.64 at 1.66 at 1.6. What have you turned off? That's right, ladies and gentlemen, you are watching me type numbers into the world's worst calculator, a Casio. That's what's happening right now. You are just sat there watching me do some basic mathematics. I'm expecting comments saying, oh, you made a mistake at this step, because, you know, I'm human and I make mistakes. But anyway, there we go. Now we need to calculate the energy, so I need to take each of these potential differences and multiply it by the charge on the electron, which is 1.6. So let's do 1.36 times 1.6. In fact, let's put 1.6 times 10 to the negative 19 first, like that. Then I'll type the times 1.36. Is there not enough battery, or is it just because I was really struggling, wasn't it? Maybe the battery's running out on it. Let's do this as E / 10 to the negative 19 joules. So I'd have to write that power each time. So this is 2.18. Let's go back. Oh my goodness me, the batteries really are running low. I'll have to run and get a different calculator. 4.2. Screen is fading like mad every time I type something. 2.54. 2.62. 4.77. That's how quickly you can get these data and how quickly you can get the table done. Now we need to draw a graph. So what are we drawing a graph of? We are drawing a graph of E, this column, versus F, which is this column. This column is going to be on the y-axis. This column is going to be on the x-axis. So let's start by thinking about scales. In our equation, E equals HF, the y-intercept is expected to be 0. I'm not interested in measuring the y-intercept, I'm only interested in the gradient, so I can afford to use a false origin. So that's nearly 7 on the x-axis, and that's a little bit more than 4. So let's go 4 to 7. So let's have a look at that. 1, 2, 3, 4, 6, 7. I'm going to go 4 to 7, which is 3. So 1, 2, 3, 1, 2, 3. So we'll have 6 squares horizontally, 6 big squares. That's 12 centimeters horizontally. I'll explain why in a second when I put the numbers in. Let's go vertically. So about 2 to about 5. That's about 3. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yes, we'll go 12 vertically. So we'll collect the numbers in a second. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So how quickly you decide what your scale should be. Energy in 10 to the negative 19 joules. And we're going to go 2. Let's put 2.00. Let's get rid of that. 2.00. I should have used a pencil. there. In fact, let's zoom out a little bit. So you can see the whole graph. There we go. Let's go 2.00. And up here we're going to have 5.00. 1, 2, 3. 1, 2, 3, 4. This is 3.00. It's 4.00. That's 5.00. Numbers are too far apart, so we've got to have some numbers in between. If we don't, then we're going to hemorrhage mark. So I'm just going to put these little notches there so I know where the numbers line up with. Apart from my mistake down here. Okay, then I wanted 6 across. I think it was 6 across. 4 to 7. Yeah, let's do 6 across. Line it up. Like this. Remember, the data points have to occupy more than half of the available space in both directions. This should do it. So I'm going to label that one there. Frequency in 10 to the 14 hertz. 4.00 all the way up to 7.00, so that's 4, 5, 6, so 5.00, 6.00, 7.00. So there's our scale, as you can see. Sensible scale. False origin. Don't need any special symbol for a false origin. That's not a zigzag or a special symbol. That's because I messed up writing the number of decimal places. Should match what's in the table. Everyone makes mistakes. Right, let's get these data points plotted then. So where is it? Did it a 4.55. So 4. There's 5, 10, 15, 20 squares between those. 4.5. 10 squares is 0.55 would be there. And 2.18, ruler out, 2.18. What I'm going to do is I'm going to just make a note somewhere because I always mess this up. There are 5, 10, 15, 20 little squares equals 1 unit along the x-axis. So 1 divided by 20 is 0.05. So each x-axis unit, I'm just writing it here, x-axis square, 0.05 times 10 to the negative 14 hertz. Not negative, 10 to the 14 hertz. Each y-axis one, we've got 5, 10, 15, 20, and 0.5 divided by 20. So on the y-axis, I do find it helpful if you do this, otherwise you're working it out every time, and that's a bit of a faff. 0.025 times 10 to the negative 19 joules per little square. I could even put per square. Doesn't matter. So that's going to help me when I plot these numbers. So anyway, 4.55, so it's there. And 2.18. So 2.1 is going to be another 4 little squares. And 8, I can go 1, 2, 3 squares, and that's probably the nearest I'll get. So that is there. There's the first data point. 4.85. So 4.5, 4.75, 4.8, 4.85. So that lines up with this bit there. Dots on the axis or anything that helps you, it doesn't matter. We're only going to be using the x's really, the line once we've drawn the x's. And then 2.42. So that's 2.50. We want 2.40, so let's go back 4 little squares, and that gives us 2.40, and then maybe we'll go leave it there because that's where it rounds to. So there we go. Third data point, 5.04. 5.05 would be there. So we'll use 5.05. We're not interpolating between the little squares. We're just putting them on the little squares. It's close enough. 2.54, 2.5. 4 would be 2 of these little squares, near enough. So that goes there. It's looking fairly straight so far. Fourth data point, 5.31. So 5, 5.1, 5.2, 5.3 is the closest we're going to get to that. And 2.62, so 2.5, 2.6, 2.625 is the closest, I think. So let's go for that. Not quite as straight as I want it to be, but not terrible. And now this last one. This last one's all the way over here somewhere, so I don't think this is going to be along the line. Let's have a look. So 6.98 is just a fraction below that. Then actually it's to the nearest small square, it's 7. And 4.77. Ay caramba. 4.75 is there. 4.775 is nearest one, so it's one little notch higher. Well, that is not on that straight line at all. Look at that. That looks like a nice straight line there, with that one that doesn't belong for some reason, probably due to my inability to see blue properly. I'm just going to change the colour of pen to make the line of best fit a bit clearer. You don't have to do that. Rotate it around. It's much easier to do a line of best fit if you draw the line towards you. 30 centimetre clear plastic ruler. I think it's going to be about there. Like that. I'm discarding this point, because I don't think it lies on the line at all. Now what I could do is I could calculate the uncertainty in V, which is just half the range, and draw some error bars. Well, uncertainty in V, and use that to calculate the uncertainty in E and draw some error bars in the vertical direction. But I'm not going to do that this time. Let's just get on with this. So let's measure the gradient. Right, that's good. That passes, I mean, the data only goes up to there. So let's use this point. Where does it pass through? There. Passes quite nicely through a point 7.00. And this is 3.75, 3.775. On the y-axis, and we're going to use a point down here. We're calculating the gradient. Let's use a point down here. That one's pretty much on the grid lines. As far apart as we can be. I could have used this, but actually that goes beyond the scale, so I'm not going to use that bit. As far apart as they can be. So this is 4.1, 4.2, 4.3. 4.30. In the vertical direction, 2.05. Just like that. Gradient calculation time. So my gradient is my Planck's constant. That's going to be the difference in the y-axis. So that is 3.775 subtract 2.05 times 10 to the negative 19 divided by the difference in the x-axis. So that is going to be 7.00 subtract 4.30 times 10 to the 14. This horrible calculator. 3.775 subtract 2.05 equals that times 1e minus 19. Oh, horrible calculator. Right, so I'm just going to put these intermediate steps down. 1.725 times 10 to the negative 19 divided by, let's do the other one, 7 minus 4.3, so 2.70 times 10 to the 14. So now 1.725 e minus 19 divided by Does it like divided? But I don't even know how this calculator does division. 1.725 e minus 19. Horrible thing. 2.7 e 14. Hey, 6.39 times 10 to the negative 34, and the units would be joules seconds. Well, that's not bad at all. It should be 6.63. So if I do 6.6, if I do that number minus 6.63 times 10 to the negative 34, and then divide that by 6.63 times 10 to the negative 34, that gives me it's only 0.4% error on that. 4% numbers. Let's say 3.6% uncertainty or error. Don't quite mean the same thing. 3.6% error. That is not bad. I didn't include error bars or anything, and I definitely discarded that point because it was nonsense. But there we go. Couple of pro tips. X's for your data points, and then mark off the points along the line, far apart as you can, and not where the X's are, to calculate your gradient. Write what those coordinates are. Some people draw lines, I do all this sort of thing, which is, pen's not working, which is absolutely, this is a red one. Some people draw lines like this, which is absolutely fine if you find that helpful for reading off the graph. Anything like this that makes it clear what you are actually doing, but just be careful that your lines are actually lined up with the grid lines, like they are there. Sometimes people do that and they'll drift a bit and it's not great. Reading the coordinates off and writing them down is probably better. Some people draw a triangle. That's fine if you find that helpful. I think this is better. Make sure the decimal places of the numbers that you record on your scales matches what's in your table. It's just good practice. Repeats are clearly laid out there. Okay, I'm happy with that. And there we go. That is measuring Planck's constant using this apparatus here. Took about half an hour in total with me explaining what I'm doing.